In the last presentation, we learned about periodic table basics, information that we can glean off of the table pretty clearly. Now we're going to look at some trends, patterns that we can find of properties on the periodic table. In this section, we will look at the periodicity patterns of atomic radius, ionization energy, and electronegativity. Periodicity is the predictable pattern by which properties of elements change across or down the period. Remember, when we go across, we will be looking at periods of elements, and when we go down, we'll be looking at groups or families of elements. One thing I want to mention is that there will be exceptions to the trends of periodicity. Each trend is a general trend, meaning that not every element is going to participate in that pattern. It's very similar to, say, a fashion trend. Let's say hunter boots are the fashion trend for spring. Everybody pulls them out when it's raining. Will everybody have a pair of hunter boots? No. Some people don't participate in that fashion trend for particular reasons. Same thing's going to happen with elements within the families and the periods. Sometimes they'll follow that pattern and sometimes they won't. We're just going to be making general pattern predictions. Our first property is called atomic radius. Atomic radius is basically the size of an atom. It is defined as half of the distance between the nuclei of two bonded atoms. So if we take a look at the example below, you see hydrogen. We know that the nuclei is a dense center region in the center, and we've got pretty good instrumentation to kind of give us an understanding of where the center of that is. So we're going to go ahead and we're going to measure the distance from nuclei to nuclei, and then what we'll do is we'll cut that in half, and that will actually give us the radius of each atom. If you look at this table, you can see the actual values of atomic radius. The unit is usually picometers or nanometers. And if we take a look at the two basic patterns, let's go across a period. Let's start with period 3. You can see that the values are 1.86, 1.60, 1.43, and so forth. So we know that the period trend is decreasing. The size of the atom is getting smaller as you go across. If we look at a group trend, such as group 1A, you can see we go from 0.30 to 1.52, 1.86, 2.31. You can definitely see an increase in the size of the atom. So we say the group trend is that it increases, and once again, the period trend is decreasing atomic size. Now, why is that? It's important to understand that the protons and the neutrons are in the nucleus, and the electrons are outside in energy levels. As the number of protons increase, we find that the nuclear charge, the strength of the nucleus, is going to increase. Remember that the nucleus is positively charged, and it attracts negatively charged particles. So it's going to attract the electrons, which are hanging out outside of the nucleus. The strength of the nucleus draws in the electrons closer to the nucleus, thus shrinking the size of the atom. So as nuclear charge increases, the attraction between the positive nucleus and the negative electron cloud increases, and this attraction is going to pull in on the electrons, shrinking the size of the atom. Remember, as you go across, we're increasing in proton number. Lithium has 3 protons, beryllium has 4, and as you keep on going to the right, that number gets larger and larger. So remember that there's a direct correlation between the proton number and nuclear charge and strength. As we go down, you will also see that the number of protons is increasing as well. Lithium has 3 and sodium has 11. But there's another factor at play here, and that is the energy levels are changing as well. We generally find that when you go down a group, the energy levels increase. For example, if we take a look at lithium, lithium has 2 energy levels. It has 2 electrons in the first and 1 electron in the second energy level. Whereas sodium has 3 energy levels. It has 2 in the first, it has 8 in the second, and 1 in the third. The additional energy levels puts the electrons farther and farther and farther away from the nucleus. And so the nucleus, even though it has a stronger attraction to those electrons because of the greater proton number, can't really act upon that because of the distance. The electrons are located so far away, and there's a lot of inner shell electrons that actually shield the nucleus from that outer shell electron, that it's hard to draw it in, and so it doesn't increase. It doesn't decrease. It actually increases in size. So the electrons are added into new energy levels. The higher the energy level, the farther away from the nucleus. And the inner electrons are going to shield the new outer electrons from the pull of the nucleus. So it does not shrink the size of the atom. It actually increases the size of the atom. Let's take a look at some examples that would deal with atomic radius. First question says, list the following in increasing order of atomic radius. And you can see that we have lithium, cesium, and potassium. If we find those on the list real quick, lithium, cesium, and potassium, you will notice that they're all in a group. We know that the group trend is as you go down, the atomic size is going to increase. So if we're putting them in order of increasing, we're going to go from smallest to largest, and that's going to be lithium, potassium, and then cesium in that order. If we take a look at the second problem, list the following in decreasing order of atomic radius. Now we're going to be looking at calcium, beryllium, barium, and strontium. Once again, another group trend. We know as we go down, it's going to increase in size. We want to go from largest to smallest. So barium will be the largest, and then strontium, then calcium, and then beryllium. Lastly, who has the largest atomic radius? Let's go to the table and we'll look at magnesium, chlorine, sodium, and phosphorus. Now we see we have a period trend, and that period trend is going to tell us that the size is getting smaller as we go across, and so the one that is farthest to the left will be the largest, and that is going to be sodium. So let's do one more quick review. Atomic radius is the size of the atom. As you go across the periodic table, the general trend is that it decreases. Why is that? Because as the atomic number is increasing, which you see in any row, the nucleus is getting stronger, which is positively charged, and it's pulling on the electrons within that same energy level, shrinking the size of the atom. When you go down, the size is going to increase, and that's because you're adding additional energy levels. Electrons are being placed naturally farther and farther away from the nucleus. Even though you see as well that the nuclear charge is increasing, that power is negated by the fact that the electrons are so far away, and the atom just naturally gets larger. Alright, second trend, ionization energy. Ionization energy is the energy required to remove the outermost electron from an atom in gaseous state. If we take a look at the periodic table here with the values of ionization energy, and once again we look going across, you can see that generally the values are increasing. Every once in a while you'll see that they will break that pattern and decrease. Remember, we had said these are predictable patterns, not every element plays the game. So we say on average the ionization energy is increasing as we go across, and if we look down you can see that for the most part the values are decreasing. So the pattern for ionization energy as you go down a group is that it gets smaller. So once again we need to talk about why. So ionization energy once again is the removal of an electron from the outermost energy level. Let's go back to what we talked about when we dealt with atomic radius. We said that when we looked at an element and compared it to another element in the same period, we noticed that the atomic numbers were increasing as we went across, and that meant that the strength of the nucleus was stronger as you went across. So think about trying to remove an electron from a stronger atom versus a weaker atom. It's going to require more energy to remove an electron from a stronger nucleus than it would from a weaker nucleus. So when an atom is smaller, the electrons are closer to the nucleus. They feel the strength of the nucleus more strongly, and it's harder to pull the electrons away from these smaller atoms. As we go down a group, once again, even though the atomic number is increasing and the strength of the nucleus is increasing as well, we talked about how electrons are being placed in farther and farther energy levels. A sodium atom has electrons in the third energy level. That is a lot farther away than, say, the second energy level or even the first energy level. So it's easier to remove an electron in a higher energy level, and so it will not take as much energy to do so. So as the outer electrons are farther from the nucleus, they feel the pull of the nucleus less, and it's easier to remove an electron from an atom, which means it requires less energy. Let's take a look at some examples dealing with this property. We're going to look at lithium, cesium, and potassium again. And you can see that those are, once again, all in the same group. And we know as we go down a group, ionization energy is going to decrease. So if I want to put these in increasing order, we will start off with cesium, and then potassium, and then lithium. In the second example, we want to look at the calcium, barium, beryllium, and strontium. So those were calcium, beryllium, barium, and strontium, all in group 2A. Once again, a group trend. We know that ionization energy is going to decrease as we go down. Thus, beryllium will have the largest ionization energy. Then calcium will have a smaller one, strontium even smaller, and barium will have the smallest ionization energy. The last example asks us to find who has the highest ionization energy between chlorine, sodium, iodine, and indium. Notice that these elements are not in a pure period or group trend like we've seen in the past. They are actually kind of scattered about. So there's a diagonal trend that we can look at to help us make this prediction. It's called the Ire of Zorro. I want you to draw this somewhere in your notes. We've got the top of the line as being I for ionization energy, the middle one being R for radius, and the lower one E for electronegativity, which will be our third trend we'll look at in a few seconds. Notice that when Zorro moves his sword to make his signature mark, anytime he moves his sword in a direction, that is going to represent an increase in the property. So a diagonal from lower left to upper right on the periodic table represents an increase in ionization energy. Thus, chlorine has the greatest ionization energy out of this set. A quick review of the property: ionization energy increases as we go across. Remember that the nucleus is stronger, it's holding on to the electrons with more power, with more strength, and so it takes more energy to remove an electron as you're going across. As you go down, it is decreasing, and that is because we're adding those additional energy levels. The electrons are being placed farther and farther away from the nucleus, and it's easier to take an electron farther away from the nucleus than it is one that is closer. We were just talking about removing a single electron from an atom. But what if you wanted to remove a second or even a third electron from an atom? This is called successive ionization energies. As long as you have the energy required to remove that electron, you can forcibly take electrons away from atoms. What you need to know is that removing more and more electrons requires more and more energy, so the cost is going to get pretty high. The remaining electrons are more tightly bound to the nucleus every time you take an electron away, and so that means that there's a tighter hold to the nucleus, and that's just going to require an extra amount of energy. Let's take a look at the successive ionization energy chart at the bottom and focus in on sodium. You can see as we go from the first removal to the second removal to the third removal to the fourth removal that more and more energy is required, like we said. But where do we see a drastic change in energy? And that's happening right at this mark right here. The difference between the energy taking one electron away versus two. Well, if we go back and we look at the electron configuration for sodium, which is 1s2, 2s2, 2p6, 3s1, we know that if we remove an electron from the outermost energy level, that will wipe away the third energy level, leaving me with the highest energy level of 2 and a total of 8 valence electrons. It's going to take a tremendous amount of energy to break that octet up, to remove one of those electrons that is being so tightly held to the nucleus in the lower energy level of 2. If you look at anywhere on the chart, you will see that there's always going to be a place, let's take a look at silicon, where you're going to see that gradual change in ionization energy, but then there's going to be that huge jump. And that's just a way to indicate to you that you're actually removing all the electrons within the outermost energy level and moving more into the inner core electrons to a lower energy level. We take a look at silicon. Silicon is 1s2, 2s2, 2p6, 3s2, 3p2. So to remove one electron, not that big of a deal. To remove 2 electrons, we completely get rid of the 3p sublevel. A third electron would remove 1 from the s, but to remove a fourth electron would put us then now at that lower energy level again. So that fifth electron doesn't want to be removed, and it's going to cost a lot of money if we're going to, or a lot of energy if we're going to remove it. All right, let's discuss our third property, electronegativity. Electronegativity is the tendency of an atom to steal or take an electron from a different atom when combining with another element. Fluorine happens to have the highest value, and francium has the lowest value, and this will help you make the prediction for period and group trends. As mentioned, we said that fluorine has the highest electronegativity value, and francium, cesium, has the lowest. So it should make sense that as we go across, you're going to see an increase in electronegativity and a decrease in electronegativity as we go down, just based on knowing those 2 points of interest. Now, why does this happen? Once again, we got to go back to the strength of the nucleus and think about what electronegativity means. It's the desire for an atom to steal or take an electron from a different atom. So it all comes back down to that nucleus. Is it strong or is it weak? Once again, we know as we go across a period that we're going from 3 protons versus 4. We know that the beryllium has the stronger nucleus. Stronger nucleus is going to pull electrons in closer. So not only does it pull in its own electrons closer to the nucleus, but it can actually pull electrons from other atoms as well. So when an atom is smaller, the nucleus pulls more strongly, and this can attract and draw an electron away from another atom. As we go down in group, electronegativity is decreasing. Remember that the additional energy levels play a role in that. Since every time we add an additional energy level to the atom, the nucleus has a harder time dealing with those outermost electrons due to the shielding of the inner core electrons. That's also going to help us explain why the nucleus is not going to be able to grab an electron from a different atom. It's not going to be strong enough to pull an electron from a different atom due to the fact of this shielding. So the larger the atom, the less able the nucleus is to attract electrons away from a different atom. All right, let's take a look at this example. Who has the highest electronegativity? And we have been given barium, bromine, and calcium. Here's another example of a pattern that is not a pure group or pure period trend. So we do once again have to look at I of Zorro. Remember that it is the third line of the Zorro signature that represents electronegativity. And we talked about whatever movement of the sword, in this case it's going up again, is an increase in the property. So as we go from lower left to upper right, that is going to be an increase in electronegativity. And so that means for us that bromine is going to have the highest electronegativity value. Notice that that trend is very similar to the trend of ionization energy. They move in the same direction. The last example would be looking at I, Br, NCl. That is a pure group trend, and we know as we go down, ionization energy is decreasing. We're getting farther away from fluorine. So if we had to put these in decreasing order, chlorine would be the greatest, then bromine, then iodine. Quick review of electronegativity. As we go across, the trend is going to increase. One of the ways to remember that is fluorine has the highest electronegativity value of 4.0 Paulings, and cesium has one of the smallest. So that would explain the decrease. And remember that it really has to do with the strength of the nucleus. As we're going across, the nucleus is getting stronger. Not only can it pull on its own electrons with more intensity, but it can also pull on electrons from different atoms and take them over. And with the decrease, which is the group trend, we know the additional energy levels are causing the nucleus to get weaker, so it doesn't have as much strength and it can't pull electrons away from other atoms.